Alrighty, folks. Our plan today, I want to finish up the 2.3 notes. We'll take some questions from 2.3 stuff if you have any right now. I'm going to briefly kind of talk about 2.4. That's a no homework section. It's just kind of for enrichment. And then I want to do a little extra bonus section about limits and composition using graphs. So that's our plan today. So I think I left off, bless you, last time on this example 9, right? Does this look right? We had just done the, okay. So it says if f of x is this piecewise function that's given, determine whether the limit as x approaches 4 of f of x exists. So to determine if a limit exists or not, what are we looking at? What do we need to show or check? If the left-hand limit matches up with the right-hand limit, correct? Okay. So the limit as x approaches -4 of f of x is going to be equal to the limit as x approaches 4 of 8 minus 2x. Why? Yeah. So if we look at, approaches approaches 4 from the left, we're looking at that part of our piecewise function, right? Now, 8 minus 2x is a polynomial, so I can just do direct substitution on this. Everybody agree? If we do the right-hand limit, that's going to equal the limit as x approaches 4 of square root x minus 4. The same reason, right? Everybody's cool with that? And again, that's a radical function, so again, I can do direct substitution there. So since those two limits match up, I know this limit exists and it's equal to 0. Does everybody feel okay there? So again, checking a limit for a piecewise function, if you're evaluating at where the two pieces meet, all you got to do is check, what happens at that boundary between the two pieces, right? Make sure the two pieces meet at the same y value, even if, they're not exactly defined there, right? So like even if it's had an extra piece that said, and at x equals 4, we evaluates to 7, did that extra piece matter? Didn't change the limit at all, right? Even though f of x evaluates to 7 at x equals 4, the limit is still 0 at x or as x approaches 4. Everybody's cool? Okay. So next theorem states, and this theorem is just used to get to the next one, says that if f of x is less than or equal to g of x, when x is near a, so in the neighborhood of a, everywhere except possibly at a, doesn't have to be at a also, then the limits of f and g both exist as x approaches a, and then that the limit as x approaches a of f of x has to be less than or equal to limit as x approaches a of g of x. So like pictorially, what are we saying here? So let's say here's a, and let's say, you know, this is f, and come on, oh my goodness, and let's say that this is g. Notice that f at all times is less than g because it's underneath, right? Everybody agree? So if I look at the limit as x approaches a for g, that's this value. And if I look at the limit as x approaches a for f, that's that value. No matter how I draw those, as long as one is on top of the other and the limits exist at a, then we can always say that the limit, g's limit has to be bigger than f's limit. Is everybody cool with that idea? Pretty straightforward if we draw the graph, but oftentimes the picture really kind of helps cement what are we trying to say here. Oh, yeah, okay, sure. Like, once I look at the picture and you're telling me that's the situation basically it's describing, well, of course, then the limits have to be, you know, also have to be less than each other, right?
Is that less than or equal to, or is it just less than?
It's less than or equal to. Yep. Yeah, so if the two touched at that exact, you know, at like one point in there, it's still just, you know, the limits have to be either less than or the same, you know, the same as to hold true. Okay, so the next theorem is the important one. And really we only need that theorem that's labeled as number 2 is really just needed to construct what we'll call the squeeze theorem. The squeeze theorem is one other tool that we can use to evaluate a limit that is indeterminate. So if you're able to set up a squeeze theorem situation, this would allow you to possibly get around one of these indeterminate limits. It's not the best way of doing it, but it can work. So what the squeeze theorem says, if we're looking for the limit of g, if I can find a function that's less than g and a function that's greater than g in that neighborhood of a, and the limit as x approaches a is equal to the limit as x approaches h, then the limit of g, or as x approaches a of g, also has to be the same as that for f and h. So pictorially, what we're kind of saying is, let's say that's a there. So let's say that this is, oops, do a better job on drawing that. Let's say that this is h, and let's call this one f, and let's say that like, oops, I thought I changed that. Now come on now, I picked the red one. Oh my dear. And let's say then that this is like RG. If I look at the limit as x approaches a for all of these, they all have to be the same thing, right? Does that make sense? If we look at the picture like that, if I have some upper bound and some lower bound and they meet, where they have the same limit at that specific value, then f also has to have that same limit because it's stuck in between them. It's like they're squeezing down on f. That's why it's called the squeeze theorem. All right. So let's look at an example. This says show that the limit as x approaches 0 of sine of 1 over x equals 0. Sorry. Yeah, the limit as x approaches 0 of sine of x squared times sine of 1 over x, that is equal to 0. So if you try to do a direct substitution, you have like 0 squared times sine of 1 over 0. 1 over 0 is undefined. How do I do sine of... I don't know what to do with that, right? A direct substitution makes no sense. So what I want to do is I want to try to set up a squeeze theorem to go around this. So whenever I have one of these squeeze theorems that involves a trig function, I'm going to start with the trig function piece and try to build out my f and h using that. So I'm just going to start with sine x. What is sine x bounded between? 1 and negative 1, right? We remember that from trigonometry. And I know that no matter what is inside my sine function, that's still just going to be bounded between negative 1 and positive 1, right? Because no matter what is the inside of my sine, the output is going to be between 1 and negative 1. Everybody agree with that? Okay. Now if I multiply, or if I compare this to what I have here, the only thing that's missing is the x squared out front. You guys see that? So I'm just going to multiply now all the parts of my inequality by x squared So this now is like my F, that's my G, and that's like my H for my squeeze theorem. Is everybody cool with the setup?
So you can just like put x squared.
Oops, I meant that should be x squared.
So you can just put x squared into like one thing.
So I'm multiplying everything by x squared. So now to figure out the limit for G, I know that that's going to be the same as the limit as x approaches 0 of f, which has to equal, let's write it this way. So I'd say by the squeeze theorem, I know that the limit as x approaches 0 of G is equal to the limit as x approaches 0 of f, which is equal, that should be h there, my apologies. And as x approaches 0 of G, which is just going to be 0 squared or equal to 0. And I'm done. So the trickiest piece is going to be setting up that set of inequalities, right? If I have that set of inequalities, all I need to do is just apply the squeeze theorem, check to make sure the limits of both ends are the same. If they're the same, then that's the limit of the middle. If they're different, what do we say? Not that it doesn't exist, we can't say. So remember, the limit in the middle is some kind of indeterminate thing. If the squeeze theorem doesn't work, like, sure they bound, but they don't, like the limits don't match in the middle where we need them to, that doesn't tell me that the f in, or the function in between doesn't match. It just tells me I don't know what it is yet. I didn't pick a tight enough squeeze, or I can't do it with a squeeze theorem. You know, like there might not be a neighborhood in which that, you know, it bounds it. So like if like my f does this, and then like my g does that, or my h does that, and I'm worried about this spot here, there's not a neighborhood in which those guys bound. So I have bad f and g, right? Or you could have a situation like, here's, like there's my g, and like here's my f, but my h goes in because the limit of f and g don't match. Well, the limit for, where'd it go? The limit for for g exists. It's there. I can see it in the picture, but my bounds, the function I picked for my squeeze theorem don't actually squeeze down tight enough to get it. So that's kind of what we're saying. If they don't match, you can't say anything about that limit for g. It's cool. Okay. So that's the end of 2.3. Squeeze theorem is one of those that we'll expect that you guys can use. I would never ask you to quote the squeeze theorem, but you should be able to use it in context. If you use it in a free response problem and you're using the conclusion, you need to state by the squeeze theorem, the limit of g of x equals the limit of f of x, which is, which equals the limit of h of x, which equals whatever, But you do need to state in words that I'm using this now if you're going to apply it. So you need to know the name, and you need to know what it does, what it can do for you, and what the conditions are to use it, right? Like, you got to know how to use it. You don't have to be able to recite it for me. Does that feel good? In general, that'll be the case in this class. There will be theorems that, like, the expectation is that you have memorized where you can use it and you know the name of it, but I don't actually expect you to quote it other than like, I'm using this theorem now to do this. Is that okay? And I'll try to make a point as we run into these things, like this is one that you need to know the name of and the conditions and the result so that you can use it in the future. And the squeeze theorem is the first one that we've seen where it's like, you must know this by name and be able to use it. Okay. Questions on these last couple of ideas here? Okay. So you guys got some homework stuff from 2.3 that we want to talk about here, I would suspect. This one is a lot more algebra-y, which is, depending on your preference, maybe a welcome change. Does anybody have, yeah, Michael?
23.
23? Sure. So the directions for all these problems 11 to 32 just say evaluate the limit if it exists. So I'm going to do these all algebraically. I think that would be the easiest way to do this. So if I look at this and I try to plug in, do a direct substitution, you notice that we get 0 over 0, right? Get 1/4 plus a negative 1/4 over 4 plus negative 4, which is 0 over 0, right? Bad news bears, we can't say anything about the limit from that. So I'm going to have to do some kind of algebraic simplification in order to cancel some stuff off in order to hopefully get around that indeterminate hurdle there. When I look at something like this where I have fractions inside of fractions like this, what do we call that type of expression as fractions inside of fractions? We used to call it a complex fraction. My trick for getting rid of that is I'm going to just multiply the top and bottom by the least common multiple of the denominators. So if I look at my denominators, I have 4x and then really 1. So the least common multiple of 4x and 1 is just 4 times x, right? So I'm going to do that as my first step. And this is typically the better option than like trying to make common denominators and like making two reciprocal and then flipping, and this typically cleans things up really nicely. So when I multiply 4 times x to 1/4, I just get x. When I multiply 4 times x to 1/x, I get 4. Oops. And then when I multiply to the bottom, I'm just going to write it like that. So far, so good. What do you notice I can do now? Yeah, can reduce those. So we'll say this equals the limit as x approaches -4, 1/4x. And now we can just direct substitute. And we have -1/60. I want to point out something about the way I've shown my work here. Notice this part keeps hanging on until I've done that direct substitution. On your tests, I will be picky about this. You need to keep the limit there until you do a direct substitution. You've actually evaluated the limit. So if you're doing algebraic steps where you're rewriting the expression, the limit has to stay there until you're ready to plug in. I will be picky about that because the AP is going to be picky about that when they're grading. Okay? Do you guys understand what I'm saying? Like if you just wrote this, I'm not giving you full marks. Okay? So if you don't write the limit on that intermediate step, if you forget those, you're going to get graded down. Now there's a maximum amount that I'll grade down for like the number of, but I am going to be picky about that. That'll be part of the grade for any limit problem, is making sure that the notation is consistent and correct. And Michael, this was yours, right? You happy?
Yeah.
Okay. Is everybody clear what I mean by the hanging on to those limits until you finally evaluate? Okay. And we'll do some more, I'm sure. I saw a bunch of hands here. Alex, did I see your hand also?
Yeah.
What's up next?
30.
30. Yes, sir. Did you like that trick, though, about like kind of clearing the fractions out of there? That's pretty slick. Makes the algebra pretty easy there, right? Had you seen that before, guys? Yeah? Okay. Sometimes I don't know the way that, the way that other teachers are teaching things. So I just curious if that's like a reasonable expectation, or that was going to be like, oh my God, you just blew my mind. So if let's start with a direct substitution. So if I plug in -4, I get 16 plus 9, so that's 25, which square root of that is 5. So I end up with 5 minus 5 in top, and -4 plus 4 in bottom. Well, that's 0/0. Okay, so we got to find some other way of doing this. Everybody's happy? So notice every time when I'm getting to one of these, I'm just checking can I do a direct substitution. If I get an indeterminate like 0/0, I'm stopping, and now I'm going to look for some algebraic thing. Do I have to write down like the work to check to see if it's indeterminate? No, you do not. But you need to check in your head before you do anything, because it's a shame to do a bunch of algebra and realize that I could just plugged in the number at the start, just been done with it. Okay. So I look at this and I see the square root piece in here. With the plus and minus, and if I look, there's not like a difference of two squares kind of factoring I might be able to do and reduce out the radicals here. This screams to me, let's multiply by the conjugate. So the conjugate would be square root x squared plus 9 plus 5. And I'm going to do that to both the top and the bottom. Notice because there's no equal sign yet, I'm not putting another limit here. The limit won't show up until I write that equal sign. But every time I write an equal sign, I'm writing a limit until I've plugged in -4, right? So when I multiply these two things out, that's really just multiplying a difference of two squares, right? So I'm going to have square root x squared plus 9 quantity squared minus 5 squared. I'm just going to simplify that kind of in my head. So the squared cancels the square root, and then 5 squared is 25. Oops. And then I'm just going to, since I'm planning on being able to do some reducing later, I'm not going to bother foiling that denominator out. I'm just going to write it as a factored form because if it's a fraction, it's got to be in a factored form to reduce later anyway, right? Notice up here, that's going to give me -16. I notice that's a difference of two squares, so I'll factor the numerator. And if I check out that fraction, hopefully you see right away, and cross out the x plus 4s, that clears my indeterminate hurdle because I notice when I plug -4 into either of those, I'm getting 0. So if I plug the -4 in now, I'm going to get -4 minus 4 over 16 plus 9 minus 5. So far, so good. So that's going to give me -8 over 5 minus 5. Notice I dropped the limit here, right? As soon as I started plugging the -4s in, limit can go bye-bye. I'm going. I can get there. Oh, yeah. Thank you. Plus 5. Awesome. Yes. Perfect. Yeah. Did everybody? We saw what I did there. I made a boo-boo in copying. And that reduces what down to like 4/5 or something? And we're good. That.
Yeah, I did that.
Don't do that. Did that feels okay? Did you do the correct first step?
I just I thought when it's approaching -4, I thought it was -2.
Oh, well, then you would have been able to plug in right away and be done. You just copied it down wrong then, basically, yeah? Yeah, that's a bummer. Who else? Michael.
I was just going to ask, because you said you were picky about writing the limit.
Mm-hmm.
Is that, since you said that like after this turn the quizzes?
I won't be picky on the quiz.
Okay, so I think
Again, like we hadn't really talked about, I forgot to mention it when we were doing this. That's okay. If you forgot, it won't be the end of the world. I'll probably just make a comment about it. But, yeah. Because we didn't see a lot of examples of like what excellent work kind of looks like. And notice here that I'm not showing every little nitty-gritty algebraic detail, but I'm showing like intermediate steps where I do a big chunk and then I do another chunk. And it should be enough that where you can look at it and be like, maybe you have to look at it for a second to see what you did, but like I should be able to see in detail like kind of what you did to go from one step to the next. But you don't have to do like silly stuff, right? You don't have to show me foiling. Like that's fine, just foil it and give me the next thing. Or like, if you do a reducing, like show the stuff crossed out, but you don't have to go crazy. You know what I mean? Alex?
Will you be picking on the homework too, or just tests?
Well, the homework I'm not grading right or wrong, right?
Yeah.
So you should get in the habit of doing that in your homework, because if you don't do it in your homework, it's going to be, it won't go well for you on the test. You'll forget because you practice doing it the wrong way kind of thing. But it's not a big deal if you're like, I already kind of finished the homework and I was definitely not careful about that. Maybe it's worth taking one or two and going through and being like, where did I miss my limits at? And like trying to squeeze them in there. Don't go crazy though. Like don't erase and rewrite things. You don't need to do that. You know what I mean? Again, like super sympathetic that like I didn't mention it and now I'm saying it and you're like, oh no, do I have to redo anything? That's on me for forgetting to mention how picky I was going to be about something like that. Don't rewrite anything. Like save your pencils, save your hand, save your time. Anybody else on 2-3? Okie doke. I had some people come and talk to me during CT also, so that probably cleared up a lot of the other kinds of questions. All right. Let's talk about section 2.4 then. So 2.4 is the precise definition of a limit. This is not an AB topic. I will give you no homework assignment on this. It's just a enrichment, like we'll sit and listen and you walk away and be like, oh, maybe I understand a little bit more how to do this or what this means than when I started. The reason that we want a precise definition for a limit is because for the most part, these things that we've done, we haven't really able to prove that our answer is correct. I mean, we write this thing down and I show you how to do it, and like we tell you this answer is correct, but like how would I go about proving something involving a limit? We need like a really technical definition in order to do something like that. And almost all of higher mathematics is concerned only with like what new thing can we discover, what new thing can we prove. It's not about computation. So in order to do that kind of thing, you need really tightly defined terms. So we say, let f be a function defined on some open interval that contains the number a, except possibly at a itself, the same lead-in that we've had for like almost all these limit things. Then we say the limit of f of x as x approaches a is L, and write that the limit is x, the symbols. For every if for every number epsilon greater than 0, there is a number delta greater than 0, such that 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. And you probably read that and like, Mr. Kulik, I don't understand a lick of what we're saying here. So when I look at this, what would you describe the absolute value of x minus a? What does that mean? This is almost like a geometry question. It's just the distance between x and a, right? So we're saying if the distance between x and a is between 0 and delta, then the distance between the y coordinate, f of x, and the limit, L, has to be less than epsilon. So it's saying, if I put a bound on how far x is from a, I also get a finite bound for how far y is from the limit. Does everybody feel okay with that? So if I look here, So what we've drawn here, that's the interval that is delta away from A. Right? This is the interval on the y where f of x is epsilon away from L. What's going to happen as delta goes to 0? As we squeeze in on the x-axis, what's going to happen to that bound on the y-axis? It's going to squeeze down also, right? So as delta goes to 0, y minus, or yeah, you get the idea, right? So let's look at an example of kind of how to do this. So it says, use a graph to find a number delta such that if x minus 1 is less than delta, then the absolute value of x minus 1 is less than delta. Then the absolute value of x cubed minus 5x plus 6 minus 2 is less than 0.2. All right. So if I look at this and I compare it to my definition, that was kind of my definition, right? I'm just writing the symbols above it. So I can see that A is 1, f of x is that cubic, and L is 2. Does everybody feel okay there? Well, I guess we can write epsilon is 0.2. So when it says use a graph, what am I going to be graphing? What would I want to graph? F of x, right? Not tricky there. Let's go maybe -3 to 3, because it has to be, A has to be in that interval somewhere, so that should be enough. And then just maybe -5 to 5, that should probably be enough. Again, L needs to be in that interval. L is just 2, so that ought to grab it. Let's make that, I want to see the whole thing just for my own sake. I'll make that 15 or something. That ought to grab it. Yep. Okay. So far, so good. Yeah, we have a graph of f of x. Okay. So what I'm going to do next is I'm going to take a look at this. I'm going to rewrite this without the absolute value. What happens to this inequality if I try to clear the absolute value? How do I rewrite the same inequality without the absolute value? Well, I need to have two ends of it, right? I think that's what you're saying, Paulo, when you said change the sign, right? So I know that if it has to, the absolute value, something has to be less than 0.2. Well, it could be between negative 0.2 and positive 0.2. Oops, forgot the minus 2 here. That was important. And now I'm going to add the L to both sides. So if I add 2 to both sides, so far so good. So now I'm going to add to my graph the lines 1.8 and 2.2. So y equals 1.8 and y equals 2.2. And I'm going to resize my my window so that I'm not looking at much more than that. So I'm going to go, say, from 1.5 to 2.5. Should be sufficient. Hit some graph. Is everybody okay there? So now I'm only caring about the part of my function that happens in between those two. So I want the So I'm going to figure out what this x value is here. And I'm going to figure out what that x value is there. So far, so good? Do you remember how to do that with your calculator? So we press second and then the trace button and pick the intersect command. So it's going to ask me 3 questions: first curve, second curve, and guess. So the first curve, it tells me, is the cubic. So I'm going to press enter. The second curve, it says, is the 1.8. So that's this line here. I'll press enter. And then my guess, since this intersects at 1.8 intersects this 3 places I can see, I want to make sure that I'm careful about where I'm adjusting to. I'm going to go right here. Oh boy, did I just goof that? What happened to my thing? Try it again. First curve, second curve, guess. Okay. So I have about 1.12. Everybody's cool. I'll do the same thing up here. So I have so second trace, intersect command, first curve cubic, second curve I'm going to press up or down till I'm on 2.2 and then give my guess right about there. Zos looks good. Press enter. And that gives me, say, 0.91. Oh, I guess it's worth, here, let's pause. Can I take a timeout real quick? Why did I pick that section that's in between the two curves? Why not pick this section or this section? Why did I pick this section? Well, remember, this problem is supposed to be the limit as x approaches 1, and the limit is supposed to give me 2. So I want the part of the function that contains kind of that 0.12. So if I wanted to, I can like make a 0.12 and have the graph plot that for me. Or I could just kind of look at the scales, but I kind of lost the x-axis there. So I'm just going to make the 0.12 here. And then I'll turn plot 1 on to plot that. So there's the 0.12. That's basically where I'm expecting where I know the limit is at. So that tells me that I want that section of my graph, right? Okay. If I look at this, so this is plus 0.12 above 1. And this guy is basically like less 0.09 below 1. So what do you notice here? It's not symmetric, right? The x is a little bit closer to one end than the other. So the question becomes, do I want the interval to be bigger or smaller? Right? Should my delta be this one or should it be this one? I want the smaller. The smaller. Yes. Yes. So if I pick delta to be that 0.09, or really anything smaller than that would also be sufficient because it's just going to make, the tighter bound on my epsilon. So let's say delta less than or equal to. But that's the idea. This would be, if you stick around to like Calc 3, you'll do like epsilon delta proofs as part of your Calc 3 course, and it'll look a little bit like this. This is a pretty easy version of that. But I just wanted to give you like a taste of what that looks like. Okay, would I ever ask you to do this on a test or quiz? No. Am I asking you to do any of this in the homework? No. Did I just ask you to sit back and enjoy seeing some mathematics that you didn't know before? Yeah, that's all. Is everybody okay? All right. I want to now talk about this idea of finding the limit of a composition of two functions when your two functions are given to you graphically. So if you have we've already done this a little bit, right? So like if we had the limit as x approaches a of like the square root of x plus 2, that's really the composition of two functions, right? That's the composition of the square root of x with x plus 2. Everybody's okay? And we've seen that, okay, to do that, we can just like push the limit underneath the radical and do that, right? i.e. that we can do that, right? Now, if we have enough continuity, that's going to work. Where this can run into problems is if you define your functions graphically, where continuity is not going to be a given, specifically at that point A. So let's look at what we're going to do here. So if I do this problem and I try to approach it naively like I did before and say, okay, well, that's just going to be the limit or equal f of the limit as x approaches negative 2 of h of x. And because h of x is continuous, what is the limit as x approaches negative 2 of h of x? Got to be. What is this limit going to be? Here's h of x. Here's negative 2. So it looks like 1 to me. Everybody agree? So then if I go to evaluate f of 1, looks like that's 1. Does that feel okay? Now everything is fine because both these functions are continuous. No big deal. Let's look at this one where we don't have continuity all the way, right? So if I say this, what do I do? Does the limit as x approaches 0 of h of x exist? No. Everybody can understand why? Because we have a discontinuity there at 0. So, okay, well, I'll just say does not exist, right? If the limit of h of x doesn't exist, I can't plug does not exist into f. That doesn't work, so that seems okay. What if we have it if we have something like this? So if I go to negative 3, the limit here, I can't plug into h of x though, right? It's not a direct substitution. I have to look at the graph. But that limit's 3. And then g of 3 is just 1. Okay, well that one works out okay. Still, Mr. Kulik, this seems like I just can push the limit inside the function and composition, and I haven't run into a problem yet. Right? They've all been relatively as expected. Let's try this one, though. So if we try to do that same thing, So here's -1. What do I say the limit is? What do we think? Well, what's the left-hand limit? What's the right-hand limit? Positive infinity. So what do we say? Yeah. Okay. Now, did I set this up wrong? What is going on here? No, I did this wrong. Hold on a second. Everybody, one moment. I thought I reviewed this well enough. Hold on. I think I'm wrong. So just let me think for a moment. I may have to come back because I think I have this all screwed up right now. I apologize deeply. One moment. I want to make sure that I have this correct because it is a little tricky here. Yes, okay. All right. So the way we did this, that's incorrect. This one's okay. And this is incorrect. All right. Let me show you why. Okay, you ready to watch? So when I get when I push the limit inside and I get does not exist, that doesn't necessarily say that the whole limit doesn't exist. Because here's why. This is tricky, so dial in, okay? If I look just the limit as x approaches 0 of f, what's happening at the limit as x approaches 0 for f? We're approaching 4 from below, right? So we would say that this is going to equal the limit as x approaches 4 from below of h of x. No. Yeah. Hold on. What's up?
Like the subscript, the negative. I thought that was only like from the y-axis.
Yeah. Hold on a second. That's still not quite right. Hold on. Shoot, I had this when I looked at this the other day, and now I'm screwing it all up. I'm sorry. Take a little break. I'm gonna. That's not what I want either. Yes, go ahead.
They actually have like they have I almost want to go in there. That's why I keep slipping.
Should we just call it that?
I mean, just give me one more minute, and if I can't find what I'm looking for, then yes.
I swear that feels so long. I feel like real friends. Like when you came back here,
Awesome.
yeah, it's just like different. There was like more like it was really like.
Oh my God. Yeah, great.
That's how I kept it in balance. That's why I was such a loss. It was in that balance, bro. I
Yeah, let's just break for today. We'll come back and do this again. Correct. Finish 2.3. There's more stuff you can do now. The stuff that was in red before. I told you to